Thank you very much for joining this webinar, CFD and our digital wind tunnel app at Core Studio. I'm Jeroen Jansen. I'm Associate Director in the London office and part of Core Studio. And today I want to show you a bit of what we've been doing recently, some wind studies, CFD, and also the actual application development of our digital wind tunnel app. And before we start, I thought I'll give a very brief introduction of Thornton Tomasetti, who we are, and Core Studio, who we are, what we're doing, let's say. Thornton Tomasetti, we have a global footprint, about 50 offices worldwide, headquartered in the US, but also actually a strong presence in Europe and further afield. And we cover quite a wide range of projects, from the super tall, the Jeddah Tower on the top left, to much more smaller, nimble, and complex geometry projects like the vessel, movable structures like the sheds, or in London, for instance, large parts of the Woodwharf development, or Hop House, which focuses quite strong on embodied carbon. And is really set into quite a historical setting right there. So quite a wide range of projects, quite wide range of practices and professions as well. So structural engineering, facade engineering, sustainability, protective design, and as well as we see today, some digital wind engineering. If we then look at Core Studio, Core Studio is really embedded within the whole firm. It's really the incubator of many different things, research and development, and as well a couple of applications that we've been developing. So this is quite a broad overview of the areas that we cover with the apps. Most of them are all starting or began some life of a question that we had ourselves, or some problem that we walked into, but they grow bigger as Construe is basically an external platform. And I'll actually show you three now very briefly before we zoom in. So one of them we've been developing is Swarm, so really a way to package your Grasshopper definitions and share them with colleagues, with designers and the likes, working as a web app. And you see the slightest change in the geometry update, but as well integrated within Rhino, Revit, Illustrator, and the structural softwares. Another one much more focusing on machine learning, artificial intelligence, is the T2D2 defect detection. So basically, on a set of images or a drone video, it can automatically detect defects, loose roof tiles, open rebar, that sort of things, and then actually having a portal that relates back to the client and actually tells them, okay, this is wrong, you should update this, etc. So we're rolling that out to commercial parties at the moment. And similar, based on machine learning, is our Asterisk tool, which basically takes any volume on the left-hand side, and then based on a machine learning algorithm, it actually gives you a framing of a building, and you can really quickly compare cost, weight, but also different shapes, different materials, steel versus concrete, different base sizes, etc. So really quickly, early design and optioneering, let's say. So that's a very brief introduction of Thornton Tomasetti and Core Studio. But really, let's focus on what we've actually come for today, climatic design and wind engineering, as we call it. And what that means is really, digital wind engineering, CFD, so computational fluid dynamics. And we've been applying this on quite a few projects so far, going from the master planning stage. So actually very early in the stage, running wind simulations, and in this case, actually trying to design, even at proposal or competition stage, trying to design with the benefits of the wind. So one of these examples is actually in the Middle East. So we've actually tried to increase the wind speed, and with that actually draw wind in and kind of cool the wind, cool the surfaces with the wind, and with that actually improve the quality of those spaces. And really start thinking of applying that in the early design together with architects, with the wider design team. So one scale is master planning. The other scale is actually zooming in much more into the individual building and looking at pedestrian wind comfort studies. So typically for this, you would run 16 directions all the way around, or 36 in, let's say, in the City of London. And then actually looking at a year-round or a seasonal comfort and of the ground plane, but also actually accessible roof terraces and balconies. And then really with the probability of the wind, so the wind blows on the left-hand side, wind blowing from a certain direction with a certain likelihood, you can then actually relate that to a category of program. So is it suitable for frequent sitting, occasional sitting, and attached to that, you can then program that for restaurant terraces, cafes, outdoor spaces, or if it goes a bit further down the line, then maybe it's only suitable for bus stops or pavement, or even uncomfortable and unsafe. That's possible as well. And then often we need to do something on the design to actually help it through planning. Another thing this is very recent, we've been starting to look at is actually, we call it healthy indoor. So actually, the age of air inside of a space, thinking about going back to the office again, and is the HVAC system actually working appropriately, yes or no? How do people behave and feel the space? And is the ventilation adequate, or do we need more fresh air? That sort of things. And you could think about offices, but you could also think about larger cultural spaces, like museums and public routes, or even airports for that matter. So that's something we've been looking at. And another aspect I want to zoom in a little bit further is actually taking this to the next level and actually looking at wind loading on buildings, right? To actually apply the CFD, the digital simulations for early stage wind loading and facade pressures, and how do we get about it? Because it's one thing for pedestrian comfort, which really looks at mean wind speeds and much longer probability patterns, whereas wind loading actually much more looks at peak intensities and sudden gusts. And that's where it becomes a lot more tricky to do that in digital studies, in CFD studies. So we've been looking at pressures on the facade, and we have quite a portfolio of buildings with wind tunnel testing, physical wind tunnel testing done. So we've been starting to compare those with our digital tools and actually develop and fine tune these digital tools to get closer to that wind tunnel result. So for instance, comparing overturning moments at the base of a tower of the CFD, the dots in the graphs are the CFD, and the graph is actually the wind tunnel report that we compare to. And here's another one, a super tall one, where actually the initial advice as well was to put a damper on top, and actually how can we design for that and actually replicate that same level of confidence of the wind tunnel back into the digital simulations. And with that as well, looking at overall facade pressure. So actually looking at the whole field of pressures, running that for 16 directions or more, maybe 36 every 10 degrees. And then actually looking at, again, so facade pressures is a step further again. It's also looking at actually probability of that maximum pressure happening from a certain angle, and that's then aggregated and mapped on the facades. And ultimately getting into frequency and damping ratios of the building. So actually looking at the acceleration of the actual movement of buildings. So every building moves in the wind, but it's the structural engineer's task to kind of limit that to acceptable, to comfortable levels, let's say, so to not move too much so that it's not perceived by the visitors. And actually, to do that, we had to take a step back. So we've actually started a collaboration with Western University. So key really for structural loading studies in CFD is the whole level of turbulence and inlet conditions, and to replicate basically air over the Earth's surface in a way. So velocity increases by height. Don't want to go too much into detail, but velocity increases over height, but there's also turbulence in the air, and that turbulence causes gusts to exceed and to appear. So it's really a mean velocity, which is important for the pedestrian wind comfort, but actually the gustiness creates dynamic peak positive and negative pressures. And to simulate that correctly into the CFD, into the digital simulations, that is key. That's embedded within the physical wind tunnel test, but it's not that obvious for CFD. So we started to work together with Western University in London, Ontario, Canada, with Professor Bitsumlak. And actually, as I said, take a step back and look at the typical cart building, the straight building, put it in the wind tunnel, look at the inlet profile, so velocity, turbulent intensity, and actually replicate that study in the CFD. So actually get a digital domain. You see only the typical square building in there, and actually measure the outcome. So measure both the mean pressure, so that's the graph at the top, but also actually the fluctuating components in that flow, and see if they match, and see with that, can we then actually get to accurate loading. And actually the whole methodology they've used, and we've been developing a bit further together, you can see actually not only the mean is very accurate, but also actually those on the bottom graph, the dynamic component, which often is lacking in many experiments, many CFD experiments. And then actually, I'll get a bit more detail into digital wind tunnel and what we want to do with that, but it's also actually the post-processing. So from the pressures of a CFD simulation, getting that back into the structural analysis toolkit of actually pressures on the building, or base moments and base forces. So we're working to kind of integrate that all together. And then, which is the thing that's quite important for us, is actually to have these tools at various stages in the design, right? To have the high fidelity, but also have the ease of use. So really at a very early stage, throw in, let's say, a single tower and look at its effect of multiple directions, but also, okay, start changing that massing. So introduce a podium, what's the effect? Or introduce 3 towers, and really with that play with the spacing. So really to have that very intuitive way of working directly into the 3D models. So we really, we developed a workflow basically. Sitting within Rhino, so sitting within the 3D design models, which then very intuitively picks up the whole geometry, prepares all of the input parameters to the CFD, starts running it, but also then actually visualizes back into Rhino quite quickly, so that it becomes a very intuitive tool, and you can actually run quite a few options back and forth, etc. And over the time, we've been developing quite a few of those tools, workflows. But this is actually a little video of the digital wind tunnel as we have it at the moment. So this is a very easy to use app within Rhino, as I said. So you launch it from the command line, you put in a few options, so your project name, project number, description, etc. and you can then create, as it's called, a new project. And then with very few clicks and screens, you can actually set up your simulation quite easily. So you see here, it picked up the layers from the Rhino model. You can set high resolution, structure loading, which directions you want to run. So for instance, 3 in this case. Terrain conditions is an important thing to set. So for instance, if you have different terrain conditions on either side of a building, you could set them up separately. And then there's only a few extra things to set up. So basically you tell it, where do you want results from? Some surfaces, some forces. Do I want to actually cut some vertical and horizontal planes to visualize the simulation results? Gives you a summary. And then at that point, it actually starts, that's all. It starts packaging the simulation and actually sending it off to the cloud and to build that. And it will then, on the next page, it will actually tell you, okay, this is a simulation. It's going to cost you this amount of money for running it on the cloud. It's going to take roughly that time. Are you happy with that? Press OK. And at this time, this is sped up, of course, but at this time, it will actually start running the simulation in the cloud for you and pull the results back when that's done. So quick view how that works. So we've hooked it up in this case with SimScale, which is the online provider, which has this nice interfaces with this workbench of CAD simulations. But actually this is extra, right? With the app, you don't have to go into it. This is just to show what's actually happening on the background. So you see that the whole geometry of the urban model is uploaded, and on the bottom left is actually running a 90 degrees, a 0 degrees, and a 45-degree case, and actually running the cases for that, and starting to get that. And we've basically hooked this up with SimScale mainly because of the solver, where you can actually almost throw in any geometry and it basically almost runs automatically. The other thing is it's actually GPU based, so it's actually lightning fast and transient. So a simulation of this, it's probably just taking, for a big domain, 2 hours. For a single building, it might be half an hour or so. And then you actually have your results back, pulling it back into Rhino. And then you can use that for visualization. So for instance, comfort on the ground and on balconies of this tower. Or for this one again, comfort, again, ground and balconies. And really what that allows us to do is both to be quick and responsive and to really work together with architects, with the design team, but as well actually to share projects amongst each other. So I haven't showed that in the video yet, but that's one of the options we want to work on, so that you can actually, when you load up the app, you actually have a set of projects ready to use, ready to visualize, and you can share them amongst teams and amongst people. And as well, the whole thing of why we've started doing that app is actually a lot of these simulations are quite specialist and therefore actually sit with only a few people, let's say 3-4 people within the office. We actually want to expand that pool, right? So as I said, at multiple times of the project, you want to run different simulations, different level of detail in a way. And a lot of those quick and dirty simulations, everyone should be able to do them almost with the click of a button, run a simulation, get the results back, and actually get a feel of, okay, how this building is performing in the wind, yes or no. And by lowering that barrier, it really becomes a design tool. It becomes part of the toolkit of the designer. And then when the level of the project develops, when it becomes more detailed and more refined, then you can also bump up the level of detail of your simulation. and you can actually look at structural loading, let's say, as well. And with the idea that when you look at loading in the early days of a project, you get a better feel of reducing loads, because potentially there is, like, if I'm comparing codified loads with wind tunnel results, there could be a drop of 30, 40, 50% sometimes. So actually to know that early on is super valuable, and it can help the design of the building go forward another step. And then again, when you're really into the detail design, then you actually do a fully fledged full detail model, which, sure, it's maybe not a $50 simulation, that's maybe a few $100, but then at least you've developed that, and then that is also ready for wind tunnel testing if you need that validation, but at least you know what you're looking for. So that's really where we want to push this, and where we see it's going next. And then with all the research and what we've been working with, the collaboration with Western, is then actually knowing that it produces the right results for this case, let's say, and for, again, this level of detail. Actually, that was pretty quick. I was been already through my slides, I think. Yes. So actually, what I wanted to do is open it up for some questions and discussions. So we have the Q&A tool on the toolbar of the webinar. So please use that, and yeah, let's see if we can get a bit of discussion going, and hopefully some of your answers, some of your questions answered. I hope that was helpful. I hope that was useful. Right, so let's kick off with the questions. I have quite an interesting one here from Andres. Do you see physical wind tunnel testing eventually disappearing? Right, so that's a really interesting question. Not sure, actually, is my honest question. I think CFD has come a long way, and we can do almost anything that you could do in the wind tunnel. At the moment, the very detailed ones, they're still quite expensive in terms of CFD. So at the moment, no, there's definitely room for both. And in a way, I even think with tools like this and design methodologies like this, by pushing this further and earlier in the design, I actually think we're going to decide for more buildings to actually test in the wind tunnel. So I think in the beginning, this will actually lead to more wind tunnel testing. That's my opinion. Because it's quite obvious for buildings, let's say, taller than 200, 300 meters, they will have to be tested in the wind tunnel, just because the code actually requires so, right? The Eurocode, for instance, it only covers buildings up to 200 meters. Above that, you need to have wind tunnel testing done. But there's a whole range of buildings between, let's say, 100 meters and 200 meters tall that actually might benefit from wind tunnel testing. But at the moment, it's not being done, mainly because of the cost of wind tunnel testing at the beginning. And is the cost of that actually justified, yes or no? So often it's been decided, no, let's not do that. We'll just stick to the code requirements. But I actually think that with validated digital tools, we can actually test those buildings earlier, figure out, okay, there is actually a 30 or 40% reduction. And with that, let's actually go to the wind tunnel test. So I think in the beginning, we'll have more wind tunnel testing. In 10 years' time, yes, maybe we do, and the code and the regulations have picked up as well with that, and we can actually use fully CFD for the loading as well. Pedestrian comfort, that's more and more accepted already, and also actually the City of London, interestingly, for the very tall buildings over 100 meter, let's say, you'll actually have to do both. You already have to do the physical test and CFD for pedestrian comfort. So I think things are changing. but slowly, let's say. The other question is, that's a good one as well, if there's any further validation done for other geometries beyond the Carg building. So ongoing, I have to say. So we've been doing the Carg building, so it's quite interesting to work with the academic world. Let's say they do live on a different time scale, let's say. So they are also very rigorous in validation and how to treat it, let's say, right? So first step is to start with this rectangular square building, because there's a lot of parameters to investigate in terms of turbulence, wind around corners, etc. Have that done well. So that's what we've shown and presented. And then we'll move on to a single building with geometry, and then to an urban development. So we're actually going through these stages at the moment, and actually much deeper. So I showed a few examples of where we compare the CFD with a graph of the wind tunnel result, but actually going much deeper into it and really comparing a wind tunnel results of that specific geometry in the urban setting with the CFD of that urban setting. So hopefully in a few weeks' time we can show you more of that. That's currently ongoing. There's already, of course, the question of where can I download that? Well, honestly, at the moment, not yet. There's still a few things to finalize on the actual app. So a couple of things to iron out. But I think we can hopefully in a few weeks' time we can tell you more about that, how we're going to deal it. Because also there's a bit of back of house that needs to be resolved as well. Because we want to connect this to whether it's the cloud on SimScale or let's say OpenFOAM locally on your machine. You'll probably need a subscription, etc. So we need to iron out a few things there, but we'll get there, and we'll let you know. Let's say. Another question is if we include the effects of building frequencies on the wind forces. Yes and no, let's say. So that's an interesting area of where we want to go, and we are going. So if I take a step back actually, and I look at physical wind tunnel for a second. So the design of a building, and certain buildings require different tests, let's say. So the most common type of wind tunnel testing is actually that you put a solid, rigid body in the wind tunnel. You measure the movement over time, the dynamic forces on the building, basically on one point on the base of the building. And you then extrapolate that back into a dynamic response and accelerations and the frequencies of the building. That's the common approach for, I would say, 90–95% of the buildings. We can do that in the CFD, and that's what we're doing at this point with these simulations. So the model is rigid. We measure the pressures either on the facade for facade pressures or on the base of the building, and extrapolate that up and find the frequencies like that. For the super tall buildings and the very flexible ones, often you do go to the more complex high force frequency simulations where, the aeroelastic simulations, where you actually really in the wind tunnel, you model the building that it actually moves and it actually flexes with the wind. And you then integrate, you measure the pressures on all the facade, and you integrate that to find the results. And by deflecting the building, it actually changes the wind pattern and vice versa. So they interact. In CFD simulations, you can do that as well. So they're called fluid structure interactions. They're a lot more complex to set up. A lot of technical things like the meshing needs to be correct, etc. Time steps. Something we're looking into for the individual cases, but I think for the purpose of the app is not really part of that part, because as I said, it's only probably not even 5% of the cases, probably even less than that. So yeah, not really part of the mainstream, and therefore not part of the app, I would see. Then we have another question. Keep them coming because they're pretty good, all of them together. So do you see a standardization of pedestrian comfort metrics for public spaces that are both understandable by the public, but also available to the public? And a similar question for age of air and indoor metrics. Yes, I think there is a further standardization happening and coming, let's say. So pedestrian comfort has always been a bit fuzzy and in the region of specialist consultants and hard to explain to the public, let's say. So in terms of rationalizing that and bringing that into a standard framework, that is really happening. And actually the City of London is pushing it quite hard. So they've launched, actually with quite a big news coverage, they've launched a year and a half, 2 years ago, a standard for pedestrian wind studies, very clearly lined out. But also they've provided the data, the wind data that you would need to use for those studies. A specific criteria for the City of London, a bit more stringent than others. And you'll now see the different boroughs of London starting to follow with that and actually implementing that as well. Because it's already for a long time actually a requirement in terms of planning within the UK. And as I said, the City of London is pushing it forward and is also recognizing CFD versus wind tunnel testing. So it's also categorizing buildings in 3 types of height. The lower height where a desktop study is fine, the middle height where either CFD or wind tunnel testing is fine and they're equal to each other, or the tall buildings where you actually need both. So that's happening. I do think we still have a way to go into actually explaining that to the public. It is putting it into those 5 categories that I showed of usage. So it is attaching that to seating spaces, walking spaces, bus stops, that sort of thing that are easy to understand. But yeah, it's coming and things are moving in a good direction. Indoor air, I think we need to, as consultants, need to work still and think about what is the metric we want to use. Age of air, I feel, is quite a good one because with that we can actually, as we've shown in the quick animation, cut a horizontal plane, let's say, and actually really detailed look at okay, the air is fresh here or not, and you can think about metrics. Let's say, if the air stays stagnant over 15 minutes, then well, that's not really good, right? That's not healthy. And also it adds to the whole airborne diseases and infection rates. Everyone is thinking, of course, with COVID in front of their mind, like 15 minutes is kind of infection time. So right, that could be a metric, but it's still, yeah, as I said, a mile off to actually get into regulation and understanding, I would say, into the public's mind. This is a really interesting question, actually. So with tools for pedestrian comfort becoming more widely available to a larger user base, where do you see the wind experts spending their time in the future? I think much more in terms of complex cases. So I think what we hope and what we hope to see with tools like this, with the app, is actually that much more of the regular cases, let's say, can be done by more people, and therefore we can, like, if I'm thinking internally within the office, we can actually share the load, right? And we can on the more complex cases, we can actually zoom in much more detailed, but also take on more of those very complex case, where now maybe we say, actually, that's too complex to simulate or to model even. Let's pass on that, or altogether, maybe it's not worth it. Let's go for the conservative method. So I think actually by opening up the toolkit, we will actually become, as a whole, probably even better engineers. And I can also see, let's say, if you this app is also meant for, if we think of it again internally, to add to the structural engineers toolkit, so that the structural engineer in a project early stage could say, it almost becomes a button in like SAP or ETABS in the structural analysis software, where, okay, this is the first sketch of a building. How does it perform with wind? So you could actually just run a 15-minute simulation, and it will give you a better answer than at the moment the code requirements, which is quite rigid, right? It's based on a square building or a cylinder or a flat football stadium, which is a dome or something like that, something typical, or a simple spreadsheet at the moment. But you can get actually a much more detailed answer earlier on, and then gradually zoom in. And then at the end, maybe you do a verification with a specialist consultant together. But it would mean, as a firm, I think, internally or externally, you could actually do more, but more precise. And with that, actually, this ties up to another question as well, like, could we even add that to the structural load path optimizations for tall buildings? Yes, I think we could. So that would probably be a mixture of the simpler simulations, the early stage simulations, with the more complex ones, where you could actually start to think about shape optimization. So looking at the loading on a building, and actually, what if I treat the corners? What does that do with the overall load on the wind load on the building? Is it going to reduce? Is it going to actually get worse? Or should I rotate the building? Which is now often being done with the super tall ones. Like, for instance, if you look at the Burj Khalifa, at some point in the design process, I remember seeing a presentation of that. They've rotated it like 30, 40 degrees to actually have one leg aligning with the prevailing wind direction. That's been done in the physical wind tunnel quite late in the process. What if we actually could do that early on, actually? So I see a lot of potential with that. And in that respect also, with making these tools available, but knowing that it does give you the proper answer in a way. Right, so how detailed can CFD get? Interesting question. As detailed as you want, I would say. So person is thinking of a project condition where perforated brise-soleil was about 1 meter in front of the curtain wall and clearly provided some level of wind blockage, but building codes don't have much guidance on allowing reduced wind pressures on components and cladding. Yes, so typically what you would do is actually at the end of a project, when you go to a mock-up stage of the facade, you would put a one-to-one mock-up in the facade, and you look at things like loading on these individual brise-soleils. I'm also thinking about whistling sounds of the aeroelastic and acoustic properties of these brise-soleils. It really depends on what you want to get, what you want to throw at it, let's say, right? So you could get to a building resolution where you just throw 200 million cells at it, and you get to a resolution of a few centimeters, and get a very accurate answer. You might need to wait 2 weeks for the answer of the CFD. So I think we're not there yet, to be honest, to really combine the levels, but at the same time, you could run a larger scale, coarser simulation, and as well a mock-up of a one-to-one scale brise-soleil system, and actually relate the two together with some computational methods, let's say, with some post-processing. So I think there's ways to deal with that, but at the same time, yeah, we're not there yet. and neither is a wind tunnel, I would say, because actually in the wind tunnel, often you would already have a scale down, a 1 to 300, 1 to 400 scale model. So you would not even measure the brise-soleil. Embedded within this question is also the building codes. They don't have much guidance, but at the same time, they also don't really allow yet for any gains that you would get from reduced pressures, right? So that's the other thing with building codes. I think they also need to be updated towards having more knowledge about the structure, having more knowledge about the pressures, and how does that translate into the actual design of a building, I would say. So even the building codes need to be updated for effects of surrounding buildings, for effects of shielding of cladding components, etc. So still a way to go. Still a way to go, I would say. But let's keep it positive. Let's say, yeah. Reach out afterwards as well if you have any questions. If you want to talk about anything, we're open to anything and to talk to each other. I'll actually leave my email address up there for a second as well. So there's one more question. Actually, we've touched slightly in a tangent on it. It's sort of load path optimization, right? So one thing which we can do with the CFD is actually looking at the shapes of the building, and in more in general, actually looking at corner effects and see how that reduces the building. The other thing is actually load path optimization. So actually, how can we use the CFD to get a better load path? And I actually see some potential there with what I've very briefly showed in the beginning, asterisk, and actually machine learning, where we can actually combine the two together and marry them up and actually push this to another level in a way that it really becomes a design tool again. So perhaps you don't even have to wait for the whole simulation to be done yet, but actually you can use machine learning to kind of optimize the shape, and with that a load path. So combining not just the shape of the building, but also with the actual structure of columns, beams, floor slabs, etc. We've been doing some, but that's detailed studies. That's not actually part of the workflow we've presented here in terms of app, but we've been looking at some more fine-grained structures like truss structures and stuff like that to actually get the loading on these structures, and with that derive actually inputs for the structural analysis models. That's something ongoing. I don't have anything to show at the moment in this presentation, unfortunately. But yeah, drop me a line, and happy to discuss that further. And see how we can push that. But I think there's definitely potential there. Have you had any success in converting optimization results to actual constructible shapes? Oftentimes the algorithm seems to output a blob that is not very easy to translate into a structural member. Good question. Well, it's really, how do I say? It's probably also how do you set up your problem and your boundary conditions in a way. It's the question: what comes first? Does the shape come first, and you validate that, or do you really let it flow open and something comes out? Yes, often you get a pretty useless blob there. That's true. Often, sometimes you also get some new avenues to walk along and figure out, yeah, what else could we explore? Yeah, a bit of trial and error, I guess, let's say, right? So yeah, what do we say? Yes, I think it's really up to the problem setting and the boundary condition, and then yeah, it's almost the old credo of garbage in, garbage out, let's say, right? So it really matters how you set it up, your problem, how you define it, and what you then do with the results. And I feel there's always some human interference and interaction necessary there. We can't fully trust on the computer as such yet. And what you often see is that actually the computer is really good, or the machine learning algorithm is really good at a hyper-specific case. To once the problem is zoomed in, it can actually find an optimal solution, or provide some answers very quickly, very efficiently. But to actually from almost like generate potential options from an empty table, no, I don't think we're there yet. Even with things like I showed the T2D2 defect detection, we've actually learned there that you need to break the problem down. So the algorithm there actually first detects, is this a brickwork, is this a roof, is this a stucco building or concrete? And then based on that, it actually calls the specific solver to solve for that specific material, and then only finds the cracks and the exposed rebar or the broken bricks or the defects in the stucco. And that performs better than throwing one big algorithm on every facade. And I feel a lot of this machine learning and a lot of this optimization is very much the same. As long as you can break down the problem quite specifically, it works. As long as you can't, that's when you when it actually the algorithm starts to break down. Another interesting question, going back to the load path optimization. Optimizing load path of structural members and optimizing the building profile for wind loading are separate problems with separate constraints for each. Do you have ideas on a workflow that would integrate both together? Yes, so I think actually we need to hook up somehow. It's not done yet, but I do have some ideas of actually. I'm going back again to the asterisk. Let's say the machine learning algorithm that gives us structural sizes of members, etc. With that, we could optimize them. That now takes a relatively static input of almost like self-weight, and then code calculations on top of that. That needs to start reading from multiple inputs. So that starts to start reading from, for instance, the CFD simulation and wind loading inputs. But that then also needs to feed back. Okay, I have my result now, and actually, based on the structural load path optimization, it's maybe better to have a cantilever here, or it's better to remove a corner there. That then needs to also go back into the CFD again. So there's a bit of feedback loop necessary happening. But by actually controlling all of these things in a geometrical environment and with APIs talking to each other, coding languages on the background, I do think that's actually possible. And we're maybe not even too far off, I would say, because we've been developing all of these things separately. So for instance, the asterisk, we have been developing an API for that. I see like the whole construe interoperability platform that we've built. I haven't showed it today, but I could see that starting to become a role, and we've been discussing that on the whole digital twin and actually having a 3D building, 3D model of a building, a digital replica that takes into account sensor data and people movement, occupancy, that sort of things. And as well integrating structural analysis, or at least machine learning structural analysis into that. So I think these things, they start to come together more and more actually, and it all becomes part of a sort of an ecosystem or a tool set of things. I think. Will there be a webinar about the interoperability platform that TT built? Yes, so a couple of months ago, almost, yeah, last year, let's say the last 9 to 12 months, we had a couple of these digital webinars organized by Core Studio as well. And we will pick that up again. So the ones from last year, they're actually posted on a YouTube channel. Maybe we should just follow up, Shannon, with an email afterwards, linking to that. But we will follow up. We will start a new series pretty soon and send some emails around. So keep an eye on this place, I would say. All right, let's do one final question there then. The question is if we, building on the machine learning and everything, if we've explored to train a model to be able to predict base loads, for example, using building data like height, width, length, wind speed, or using an image of the exterior profile of the building, for example. That's interesting. No, not yet that far off, let's say, the image of an exterior profile. Don't think so. Relatively simple building data like height, width, and length, actually, yes. So again, the one video of Asterisk that I showed is basically picking up a shape and a core. So sure, there is a little bit of base information there. But then it will give you actually the whole framing. So it dices it up into, in that case, it's relatively prescriptive, right? So we tell it, I want the floor-to-floor height and the base size, and it gives you member sizes. But we've actually also started to break that down into individual components, right? So to just have a load and give me a member back, right? To actually get individual outputs, and with that it becomes much more modular and much more flexible. So I think that's all possible, and something we are exploring. So we're also exploring and trying to. Some of my colleagues are actually looking at how do I say? Let's say streamlining the whole gathering and organizing these trained models, right? So what if you could actually train your model or use pre-trained models by a data dashboard, let's say. So you upload your problem, and based on some models that other people have run, then it's maybe just a little add-on and you can get your optimization back. So yes, definitely something for in the cards for the coming months to have a look at and see how far we can push it. Yes, is it putting in wind loads, or is it actually just having an image of a section of a profile of a building and it gives back the load path optimization? Yes, that's super interesting material. Definitely something to look at. Thank you. I think that was a real good question to close this off. Thank you very much. Thanks for joining. Thanks for your attention.